Our next presenter is Dr. Everett Joseph. He is the Director of the University at Albany's Atmospheric Sciences Research Center and SUNY Empire Innovations Professor in Atmospheric Sciences. Dr. Joseph has conducted extensive research observing the role of aerosols and gases on climate and weather, from field observations in the mid-Atlantic to the marine expeditions across the Atlantic Ocean. He is also co-principal investigator for the New York State Mesonet. Dr. Joseph.
Thank you. So what I'm going to talk about today is it's an interesting project that we're fortunate to have here at the University in Albany, and our international partners in Taiwan. It's a project that's funded by the National Science Foundation and also by the counterpart agency in Taiwan. And I think the takeaway from this is sort of view it as this pilot study that we're doing. And the previous panel was a sort of setup, a good setup for this, in that what we're really doing is sort of working interdisciplinary. We're focused on extremes and how extremes are increasing in frequency related to climate change, anthropogenic and climate variability, and the impact of that, and the impacts of that, and how we respond to that, and how we become more resilient to those increasing trends of extremes. And what we're really focusing on in this project is, in this pilot project, if you will, is how do we work interdisciplinary? In the last panel talked about, the future of climate research is working interdisciplinary across scales, but it's how we work interdisciplinary within atmospheric sciences, but also with social sciences, to improve resiliency, and also work, with, and also how we in the university, how we institutionalize this to train this sort of new paradigm of thinking of how do you address this. And so that's the takeaway. I'm going to go into a lot of details, in this talk, but that's the takeaway that I want you to have from this. So the project is building extreme weather resiliency through improved weather climate prediction and emergency response strategies. And again, it's the program is a partnership for international research and education and education project, and our international partner is Taiwan. Very quickly, we have a number of institutions in the United States that are partnering in this project, university as well as federal and state partners, and in Taiwan about 6 or 7 institutions, again, academic institutions and government institutions that are in this. It's a small project, but it's big and it's complex and big for a grant project. We have about 28 faculty that are participating in the project, and equal numbers on the Taiwan and U.S. side. I'm gonna buy some time. Chris set this up very nicely, and so I'm gonna buy a little time here, which I desperately need. But the one thing I'll say is that if we looked at East Asia. So again, what I want to do is I talk about the Northeast U.S., but also talk about East Asia and talk about Taiwan, because that's really this project. But when you look at similar, it's a mixed bag in terms of when you look at Taiwan and these trends, and simply because it's a small island that sits, within a larger region. In a larger region, we see these trends, but in the island itself, we don't necessarily see these similar long-term trends. Taiwan sees about 4 typhoons. Their water supply is primarily from typhoons, and they see about 4 typhoons a year, and so that's what impacts them. Oops, what happened there? And again, I think Chris talked about a little about this. That plot showed the trends in heavy precipitation over the Northeast, over the last 50 years. And this is showing 2 different climate scenarios of what to expect in the future. And, we see varying, depending upon what scenario you look at, one's a low scenario and the other is a high scenario, and we see different frequencies of extreme precipitation. Not sure why that's happening. So the challenge is we're focused on heavy precipitation, extreme precipitation. Roughly 96 million people a year are affected by these extreme events. At a cost of billions of dollars, tens of billions of dollars, and that impact is increasing. And so there's some challenges out there. Understanding the lack of understanding, if you will, of these weather extremes, particularly on a regional scale, and their relationship to the larger scale circulation and climate. So there's a need to understand that better. The other part of this project is we're focused on predictability, the predictability of these events, and then decision making, for these events when they occur, and their impact. So I like to use this plot because what we're focused on again is really an interdisciplinary approach to risk management, right? And so this is an illustration from an IPCC report that sort of shows the magnitudes or the dependency of disaster risk on a number of factors. One is on climate. And this morning we talked about climate variability. And so these are 2 plots here that shows the probability density distribution of temperature events in 2 different climate states, or 2 different states of climate change. One is natural variability, and the other is a shift, if you will. And so that leads to weather and climate events that produce disasters, if you will. But the scope of the disaster, if you will, depend on other factors. It depends on our exposure and our vulnerability. And what determines our exposure and vulnerability is our adaptation to these events and our disaster risk management. And so what the work in this project is focused on is sort of focused on this disaster risk management, which involves, one, understanding these trends, the predictability of these events, and the decision making. But also it involves, and this is what I like about this project, it also involves training the next generation in this new paradigm of interdisciplinary research. One, within the area of atmospheric sciences, but also with social science partners as well. So we have a number of objectives. Again, understanding these trends and the relationship to climate, specifically in the regions of study, improving predictability, and then interdisciplinary training and across emergency management, atmospheric sciences, and social behavioral sciences. So I'm just going to walk through a little bit. And the way we sort of manifest these objectives in the project in these different parts. This is sort of the trend part. No idea where this. So we manifest this in the project in these 3 different parts. This is sort of what we call the trend part, this is the predictability part, and this is the decision-making and response part. And I'm just going to walk through very quickly each of these parts in terms of what we're doing. This is a plot from a recent study from the National Academy of Sciences on attribution. How do we attribute various extreme events to climate change? Over here, we're sort of looking at how well do we understand, can attribute the event to anthropogenic change, and here's how well do we understand the type of event to climate itself. And what you can see here, these are different types of events. What this study is suggesting that extreme cold and warm events, we have a reasonable understanding, and we can attribute that to anthropogenic climate change. But as we go down, we see extreme precipitation events, tropical cyclone events, and convective, smaller scale convective events, we have less understanding and we have less ability to attribute that to climate change. And so our work is really right here, trying to improve our understanding of that and our ability to attribute that to climate change. Let me see if I can do this slide transition without, there we go. And so again, the first objective is sort of this trend part. And so what they're doing in that work is essentially studying the types of weather systems, that result in these extreme events, and how they might change in the future. And it's really classifying that to these types of systems that occur. And Chris talked earlier about these various scales and the interaction amongst these scales. And so this is really detailed work using observations, using models to sort of classify these extreme events that occur to these weather systems and how these weather systems are changing with respect to these larger scale climate events. And it's really detailed studies. And then taking what you learn from that and applying that to data from climate models. And again, as mentioned in the previous panel, that's where we really need to go with this type of research. And for example, this is a picture of Taiwan in that region. And as you can see, there are a number of events, and Taiwan is here somewhere. It's a small island. But there are these larger scale features and synoptic scale features that impact precipitation. And this is just illustrating that. There's a Pacific high, East Asia monsoons, Siberian high, MJL. And so all these things interact on different scales to really impact the precipitation that occurs in Taiwan. And so it's really looking at these extreme events and their association with. The second objective is the predictability part of it. And we talked about predictability in the last symposium that we had, but I'll go through it a little bit here. And this will allow me to bring in Mesonet a little bit. Be remiss if I don't bring in Mesonet. But what we're doing, so this is a cartoon, if you will, of how we do predictability on a mesoscale, on a weather scale, if you will, a local weather scale. And this is a cartoon of an ensemble experiment. And essentially what we do, the uncertainty in these forecasts that are produced by these models are really in what we call the model physics. So how the atmosphere processes, how, for example, clouds process radiation, how it processes energy and phase changes, and how we do that. There's a great degree of uncertainty there, and then also how we initialize the model, how we apply observations, the current state of the atmosphere to the model forecast. There's uncertainty in how we do that, and so in this research that we're doing in this project is really studying how to do that in a way that really captures the uncertainty. And so, for example, in terms of looking at model physics, we're really, for given events, we're trying to capture that uncertainty in given events and then providing that to the model to generate these ensembles that we're doing. And ensembles are just different rendering of forecasts based on changes, uncertainty in physics or initial conditions. And so as you can see in this cartoon, what we do is we sort of establish this domain. Again, it's over Taiwan. And we provide these different initializations or different physics. We conduct these ensembles. This is a 56-member ensembles, and then we're able to provide different rendering of a forecast. And then we can conduct statistics with that, and that's where we get our probabilities from. So this is an example of the New York State Mesonet, where we're conducting some of this research with the Mesonet, and we have our 108 sites already up and are operating, and we're using this. And so what we're doing is we're conducting these experiments where we're running ensembles with Mesonet data. And I won't go through the details of it, but basically what we're doing is we're taking data with and without Mesonet data, and we're running these ensemble experiments and see what the impact of the Mesonet data on these ensembles or unpredictability of certain events. And this is just a quick experiment. And again, this is just to show, we're actually showing already scale. When we put Mesonet data into, this is horizontal winds, when we put mesonet data into these ensembles, we're actually seeing better skill from the forecast by putting mesonet data in. And we're looking at winds, we're looking at temperature, surface temperature and surface winds. This is just a 2 or 3 day, a 10-day event, and so, we want to do this experiment over longer time frames to really see what the efficacy is or the impact is of mesonet data. And the last part, I have two more things, two more parts. Objective 3 addresses sort of decision-making and response research. And we have a group on the U.S. side and Taiwan side of social scientists, emergency managers that are doing this work, and they're really focused on decision making. And what they're focused on is, narrowly focused on, is looking at how emergency managers make decisions with uncertainty. So impact research can be all over the place. People look at communication, they look at a lot of different aspects. What we're really focused on is how decisions are made by emergency managers with uncertainty information. So it ties back to some of the work that we're doing in terms of the predictability and in terms of the trends. My timer is going off. So we conducted an experiment. Our social science group conducted an experiment, one of the first experiments this past summer, at NOAA, at what's called a NOAA hazardous weather test bed. And the NOAA hazardous test bed it occurs in Oklahoma during the severe weather season in Oklahoma, and NOAA brings stakeholders from all aspects. They're forecasters, emergency managers, social scientists, to be a part of this test bed and to test new forecast tools, and also to look at how it can sort of incorporate social science into the forecasting. And our group was a part of that this summer. Essentially what they did was, again, they're looking at decision-making with uncertainty information. And so the experiment they conducted was to look at some new tools by NOAA that provide information, probability information. And this particular tool is called PHI, it's Probability Hazard Information System. And what they did was they looked at forecasters and emergency managers as they use these tools and the kinds of decision-making they're able to make, and look at their preferences for tools. Look at more standard tools, text-based tools, and look at these graphical tools. And they have some preliminary results. They're analyzing the data right now, but what they found was that emergency managers had more comfort with numerical information, graphical information, rather than text information, and information that provided uncertainty. They had more preferences when that information was provided to them in certain ways. But they also found, and this is really preliminary, I got some of the results from them last night and they were hesitant to give to me, but they also found that their decision-making sort of was a function of different types of events as well. And so that's an interesting data set to look forward to as they tease out the data more and what they find in that. And finally, time's up. My last couple of slides was, one was just showing the observation systems that we're using. Obviously, we're using measurement. I mentioned that. In Taiwan, Taiwan is a great partner because their meteorological resources, they have very significant resources in observation systems and models and also practitioners. And so they're a great partner in that respect. Finally, the thing that I was going to talk about last was some of the education work we're doing. Again, what we're doing is we're developing common courses. We're developing capstone courses that involve atmospheric scientists, emergency managers, and social sciences to talk about, to look at these issues across scale, so that the atmospheric scientist is thinking about what information the emergency manager needs, and the emergency manager is learning about what information that the atmospheric scientist is providing them. And so we're developing those. It's also, so it's interdisciplinary and it's international as well. That's another part, sort of, providing, experiences with cultural differences. An interesting thing in Taiwan, again, I say that they experience 4 typhoons a year. So they have adapted to that, and which is in contrast to us. In New York, we don't experience 4 hurricanes a year, and so they're more adapted to that environment. And it's kind of bittersweet for them because that's where they get their rainfall from. So if they don't get those 4 typhoons, if they get 1 typhoon a year, they're in a drought situation. So that difference is an important difference to understand in terms of how we go forward and how we adapt to these extreme events.
Our next presenter is Raymond O'Keefe. He is the meteorologist in charge at the Albany National Weather Service Forecast Office and has been in that position since April of 2010. He's responsible for the overall leadership and management of that office. Prior to that, he served as the warning coordination meteorologist in Albany for 6 years. Ray holds a Master of Science degree in meteorology from the University of Wisconsin at Madison and has also worked at the National Weather Service headquarters in Silver Spring, Maryland, and also forecast offices in Buffalo and Detroit. Ray.
I'm not sure what happened here. Oh, you got it. Okay. Kevin's coming to the rescue here. Yeah. Don't start the clock yet. Everett. I think he might have hit the off switch. Ooh, power came out.
So we're just rebooting the computer now. If I could sing or dance, I'd do it to entertain you, but you probably wouldn't enjoy that. So I think we're here.
Everett, you had 52 more slides. Right. All right. We're ready, and now we're going to be weather ready. All right. Okay. All right. Thank you, Paul, and thank you for all attending here this morning. I'd like to thank the Rockefeller Institute and the Department of Atmospheric and Environmental Sciences for the invitation. So I'm going to talk about becoming a weather-ready nation. So I guess the first place to start is, what does that mean? What does it mean to become a weather-ready nation? Well, it's about building community resiliency to increasing vulnerability to extreme weather events. Back on May 10th, 2008, a destructive tornado stretched from Oklahoma to Missouri. It was on the ground for 98 minutes, 77 miles. It was rated EF4, which is a violent tornado, and it killed 21 people. Of the 21 people that died, all of them had at least 15 minutes of lead time with a warning before they were killed. And this concerned the National Weather Service greatly. The warning process seemed to work pretty well, yet we had 21 people killed. So there was a service assessment team convened to go out and investigate this event, and I was fortunate enough to be a member of this team. Also on this team was Dr. Burl Montz. At the time, Dr. Montz was a geography professor at Binghamton University. She's still a geography professor, but she's at East Carolina University. And this was one of the first service assessments, maybe not the first, but one of the first that included a social scientist on the team. So since then, in the intervening nearly 10 years, the National Weather Service has included social scientists on several service assessments. We've convened workshops with meteorologists, emergency managers, and social scientists, all with the aim of improving the warning process. And over those 10 years, we've come up with some findings. The first one is that people typically do not respond immediately to the warning message. And this was borne out when we did that survey it was Missouri where we did much of the survey. So we, the team, including Dr. Montz, we'd walk around communities that were impacted by the tornado, and when we came upon people, we'd talk to them. So we came upon this one house that had suffered some slight damage, looked like EF1 type damage, but I suppose if it's your house, it's catastrophic damage, right? So there was an old timer out front on the lawn, and we went up to him and started talking to him. We said, sir, is this your house? Yes, it's my house. And it looks like you had some tornado damage here. Yeah, I did. So were you here when the tornado happened? And yes, I was here. So did you get the warning? Yeah, I got the warning. It came in on the TV. I heard it on the radio. Okay, so what'd you do? Well, I went on my sofa and sat down and waited for the tornado to go by. So that's not the response we're looking for, and that suggests that, we have a lot of work to do. Another thing that we found out is that the public response to a warning is a function of the credibility of the organization issuing the warning. And the National Weather Service is a science-based service organization. Everything we do is based on science, and it's our belief that the credibility of our warnings increases as our understanding of the science increases. And so we're fortunate here at Albany, at the University at Albany, that the National Weather Service and the Department of Atmospheric and Environmental Science have had a strong collaborative relationship on research for many, many years. In fact, last week we concluded our 17th operational research workshop here, where we bring together students, professors, meteorologists, the media, emergency managers, to talk about the latest findings in weather and water research. And you can see up here, we had several presentations, and two of them from graduate students, Molly and Luke, pertain to Irene. So we are studying some of the most complex and difficult meteorological and hydrologic questions here in the Northeast to better understand them and to improve our warning process. The National Weather Service, taking this 10 years of social science research, is looking at the warning process in general and the forecast process in general, and seeing how we can better stimulate a response to our forecasts and our warnings to make the nation weather ready. So I want to talk to you briefly about three initiatives that are ongoing now in the National Weather Service. The first of them is hazard simplification. You can see this map. This is November 6th of this year at 10 o'clock at night. It's a map of the United States, and not too much going on. But in spite of not too much going on, you can see at the bottom there are 24 alerts out. By the way, when I say alert, I'm talking in the National Weather Service jargon. An alert would be a watch, a warning, an advisory. A watch is issued with the possibility of the event occurring, the event being a warning event with a 50% likelihood of occurrence. A warning implies a threat to life and property, and that's issued at 80%. An advisory is also issued at 80%, but that's at a lower level, a nuisance. So in spite of a pretty quiet night, we had 24 alerts out on that night. Now there's a lot going on this slide here. There's a blizzard warning out, there's a hurricane warning out, there are flood warnings out. And our response that we're looking for from people when they get a warning is to take action. If we have dozens of warnings out, are we confusing them? Are we making it very difficult for them to take action? That's a question that we're addressing in this hazard simplification process. Now, on this particular day, all of these watches and warnings and advisories may have been warranted. This was October 29th at 11 o'clock in the morning. This was 8.5 hours before Sandy hit New Jersey. So in this particular case, maybe it's appropriate to have this number of warnings out. But ultimately, we've come to the conclusion that we have too many alerts. Here's the Weather Service periodic table of watches and warnings and alerts. And I'll save you the trouble. There are 122 of them up there. It's too much. So the simplification process is trying to go about and reduce the number of watches and warnings. I see it. Okay. All right. So the Weather Service is taking two roads to simplify the process. One is called repair, one is called revamp. So the repair process is a nudge in a better direction. It's taking something like this with all of these different watches and warnings and simplifying it down to 4. We have advisories, watches, warnings, and we've added emergencies. Emergency means, hey, this is the big one. Get ready. The other direction we're going at is to revamp our process, to throw out the advisories, to throw out the watches, to throw out the outlooks, and to stick with warnings. And more importantly, if you look at the right-hand side of that, you'll see impacts. We're going away from talking about words like warning to impacts. What does it mean to you? What does it mean to the citizens when this particular event happens? So more of a focus on what will happen to you. And that way, our hope is, our expectation is that people will take action if they know what they can expect. So our second initiative we have underway is a probabilistic snowfall experiment. I think we all here in upstate New York can agree that snowfalls have big impacts in our area. And we know that weather forecasts are inherently uncertain. For instance, we have the chaotic nature of the atmosphere to deal with. We measure the atmosphere, but we don't take enough measurements to exactly specify the state of the atmosphere. And we run computer simulations of the atmosphere that are getting better and better. But at the end of the day, it's Mother Nature that provides the solution. And we don't know exactly what that solution is. And we also know that demand for snowfall forecasts are increasing. We know that we live in a mobile society. We know that there is, on the roads in fair weather, there's a lot of traffic out there. You throw some snow down on the ground, and we can create chaotic conditions. So, in terms of weather forecasts, we're kind of faced with a dilemma. People want information sooner, but that increases uncertainty. So we're in a balancing situation here, and sometimes the whole thing gets thrown out of whack, and we are really challenged as to come up with a weather forecast. So the probabilistic snowfall experiment seeks to kind of address some of these issues. Historically, what we've done as an agency is to issue a point forecast or a small range forecast for snowfall. And here for Albany, you can see we're forecasting 10 to 14 inches. That's typically what we've done. In our new probabilistic snowfall experiment, what we're going to do now is offer a range of forecasts from a minimum range to a maximum range, and then a most likely amount, which would be our official forecast. That will be our probabilistic snowfall experiment. Now you'll notice that this is, I'll tell you, it's the Washington, D.C.'s Weather Service Office graphics. You know, last year was a horrible winter for snow, and I guess I've editorialized on my love of snow by saying how horrible it was last winter. So I'd love to show you some slides from Albany, but we didn't have any really last winter because there wasn't much to talk about. This experiment has been going on for several years on our coastal offices. The National Weather Service office in Washington was one of the original offices to do that. So hopefully in the coming year, we will have that information. So we're hoping that here with communication of uncertainty by providing a range of forecasts that individuals who may need to know a minimum amount or individuals who may need to know a maximum amount will get that information, and that way we'll reduce the surprise factor when it comes to snowfall forecast. The final initiative, Winter Weather Severity Index, Winter Storm Severity Index. Typically, when we, the National Weather Service, have issued warnings, we've issued them for snowfall accumulation. But we know that snowfall storms provide more than just accumulation when it comes to impacts. There's wind, there's temperature, there is time of day, time of year. So not all storms are the same. Some of them, if they come at rush hour, you're not going to make much headway at all. You're just going to be stuck in the snow. On the other hand, if they come maybe at 3 o'clock in the morning and you're out driving around, maybe you'll make some progress. So we're hopeful that this winter severity index will assist several different groups in different ways. For weather service people, weather service forecasters, it'll provide situational awareness. For the general public, we're hoping it provides societal impacts and actionable information for our partners. This is the index here. It goes from none to extreme. Here's a picture of Washington, D.C. under the gun, and an up-close image of Washington, D.C. under extreme conditions. This was the blizzard last January. And we also forecast, what you see for Washington here on the right is the composite, but we also forecast the components too. How much snow is going to fall? What's the potential for blowing snow? What's the potential for snow accumulation, snow load? So those are available for you as well. So in wrapping up here, I'd like to invite all of you to become a part of Weather Ready Nation. You can do that by becoming a Weather Ready Nation ambassador. And the way to do that, you will be able to help us, help society, make society change through collaborating with the Weather Service, promoting Weather Ready Nation messages, and serving as an example. These are some of the organizations that are currently amongst the 2,500 Weather Ready Nation ambassadors across the country. And my last slide here. So the director of the National Weather Service, Dr. Louis Ussolini, loves Weather Ready Nation ambassador. He really, really loves it. And interestingly, he's coming here to Albany on November 29th to visit the university and also my office. He is my boss of bosses. He's the big boss. And he loves Weather Ready Nation Ambassador Program. So it'd make me look really, really good if when he walks in the door, I can say, hey, Dr. Ussolini, guess what? I just added 50 Weather Ready Nation ambassadors in the last 2 weeks. So with that, if you want my name, it's up there, and the location to get Weather Ready Nation ambassador information is there too as well. I thank you for your time and appreciate your presence here. Thank you.
Thanks, Ray. We'll set up a line over here for everyone to sign right up. Our next presenter is David Vallee. He's the hydrologist-in-charge at the National Weather Service Northeast River Forecast Center, which provides detailed weather resource and life-saving flood forecasting services to the National Weather Service forecast offices and the hundreds of federal, state, and local water resource entities throughout the Northeast, including here in New York. David has worked for the National Weather Service for 29 years and has extensive experience leading to hydrometeorological forecast warning operations and directing weather research and training programs. His research activities span a variety of topics, including flooding and severe weather forecasting. David.
All right. Good morning. Thank you. Now we will see if I have any better luck than my two predecessors here. All right. Okay. Yeah, we can only hope. All right, everybody, fingers crossed. And presto. Please. Please. Excellent. Okay. Well, that's too bad. It's a little grainy on you. So I'm going to take you down what I think is a pretty good snapshot of what we want to do with water resource services and forecasts in our organization over the next 5 to 10 years. Yes, 5 to 10 years. It's going to take us a while to evolve the services that we're going for. What you're seeing here on the left is an example of our current hydrologic forecast, where we have specific predefined forecast locations that are tied to an operating river or stream flow gauge, typically owned and operated by Corps of Engineers or the U.S. Geological Survey in most cases. It's information that is very point specific. It is very deterministic. There's no association of uncertainty with that. This is where our forecast services have been on the river forecasting side for decades. Now, it's not to say that it has not served us well, because we have worked with local communities. Here I use the example from Hartford, where we have a pretty good understanding of what the impacts will be and the timing and the types of activities that the state and local entities have to take when we're forecasting a flood on the lower Connecticut or on the lower Hudson or on the Schoharie, et cetera. But this is very point specific, very deterministic, and there isn't much more information that we can provide, such as uncertainty, to help understand what's driving this forecast and how high or low we could be and where the error bars are. So that affects decision making, because you really wind up hanging all of your activities on one single piece of information in a moment of time. Where we are hoping to go is the loop that you see here on the right, which is a simulation from our new national water model. This is going to take our forecast services into a whole other dimension, where instead of dealing with specific gauged locations, in my service area we've got over 200 of them, we're now going to be looking at taking this down literally to the street level, over small catchments of less than a square mile to several square miles in size. This is why I said at the start, it's going to take us several years to kind of build this capability and capacity. And more importantly, the big challenge will be working with you folks on how do we best wrap this up into what we call actionable information. How do we make this as useful as possible, as quickly and easily accessible, but most importantly, understandable, to effectively get people to move or make decisions, be it a short-term instantaneous drop of a half a foot of rain in an hour or two, and what that means to a watershed, to long-term water planning, such as the folks at New York City DEP, when they are challenged with having to manipulate the water across the multitude of reservoirs that they utilize to provide drinking water to the 9 million people of New York City. So what you're seeing on the right is a simulation of Hurricanes Irene and Lee, the back-to-back events which really laid waste to so much of western New England and the eastern third of New York State in 2011. Quite a different picture. Here you can actually see in the loop the evolution of the first impulse of rainfall coming up with Hurricane Irene on August 28th and 29th. You see that big pulse go through. The colors indicate the volume of water. And then just a few days later, you see the second impulse come across, which is associated with Tropical Storm Lee. So a glance into the future. I'm going to start by giving you an idea in more detail of the impetus for change, what's driving this organizationally in NOAA and in the Weather Service. And it really hinges on the stakeholders. We've spent multiple years going out into the communities, to the watershed associations, to the water managers, to the coastal interests, and asking them the tough questions and listening to them, more importantly. They have helped over the last 4 to 5 years drive where we are going for hydrologic forecast services. And again, it's going to be moving from this point-specific information to very high-resolution, street-level information for water resources, hopefully leading to a far more prepared and resilient community when the big rains and the big droughts come a-calling. So our forecast services for decades now at the river centers have been wrapped around modeling watersheds around 100 square miles or greater in size. In doing so, typically on 6-hour time steps. Now, atmospherically, we know that's not how nature works. She dumps rainfall, as Long Island saw several years ago. She can drop a foot of rain on you in about 8 or 9 hours. Or in the case of Irene, where in 9 hours we had over 15 inches of rain come down. So we are somewhat limited because of our model architecture, or at least where we've been over the last several decades. But it has served us very well. It has allowed us to produce seasonal extended flow forecasts for reservoir inflow and water management. It has allowed us to provide forecast services at over 4,500 locations nationwide. It is currently anchored by soil moisture models and snowmelt models that are decades old. So because of our architecture, we've been very limited to be able to really expose and tap the science that is out there. The better understanding and the more physically based ways of modeling the movement of water out of the atmosphere into the ground and into your rivers and streams. One of the significant limitations is that we really don't do much for the coastline right now. We do not link the movement of ocean water into the river system, or that movement of fresh water out of the river system into the coastal estuary. That is one of the driving and key points that our partners have driven us toward, that you've got to move toward higher resolution, probabilistic forecast information that deals with the delicate coastal riverine infrastructure. And it's not just flooding like you see with Irene or Sandy. It's water quality issues. It's the amount of salinity going up into freshwater estuaries as much as it is ocean acidification and changes in the entire water column structure that's affecting habitat and fish and so on. So that is one of the impetuses for change. The second one, based on the success of these 3 conferences in the last 3 years, has a lot to do with the increase in extreme events on both ends of the scale. As you've seen here in New York and New England, we are certainly on the wetter side of that equation, and it has really been the extreme precipitation events that have driven so much of our anxiety. We have aging infrastructure that is not designed for the rainfall that we're receiving these days, and that's led to this increased urban flood risk. So from a weather service and water modeling standpoint, we have to be able to move into this arena to better inform our society on what to expect when we have these horrific rainfall episodes. Congress instituted a study through the National Academy of Sciences to look at the National Weather Service hydrology program several years ago. And in this, they singled out the fact that there are significant gaps in our observations, significant gaps in our modeling and our scientific understanding of the water processes. And that if we as an organization are going to make strides forward, we have to tap the science and we have to integrate this into our modeling capability to provide new, refreshed, and far more informative services to the nation. And then you have the personal stories. We all lived through Irene. I did, running the Northeast River Forecast Center. And it was a type of event where, to a degree, we did an amazing job. But when you bring it down to a local level, there were points along the way where we failed miserably, in no fault of our own. I'm going to read these 2 quotes because to me they do speak volumes of this dynamic we're involved in. From the State of New York Office of Emergency Management, as part of the Irene assessment by our agency, he stated, had it not been for the proactive posture of the National Weather Service Albany staff and the accurate and timely information provided, the cost in human loss would have been devastating. So in his mind, we as the National Weather Service, with the tools we had at the time, did an outstanding job to position him to make the decisions necessary to protect his life and property. But if we just hop over the border to the town selectman in the town of Rochester, Vermont, it's a very different story. He stated, "We had no warning saying it would be so bad. I knew it was going to rain a lot, but I thought it was going to be the kind of rain that would test the patch I just put on my roof. I had no idea it would be the kind of rain that would wash away my neighbor's house." That's a very telling story. Now, it may be a pipe dream to say that someday I can get him to that level where we have truly captured the magnitude of tomorrow's event with the specificity to make him understand that we are talking about his house or his neighbor's house. But we've got to move in that direction if we're going to provide our communities with the information they desire. It all started with stakeholders. We began stakeholder engagements about 8 or 9 years ago, working first with large watershed commissions like the Susquehanna, the Hudson, the Delaware, moving out west to the Russian River and the large water issues that they contend with in the west because of a lack of water. But over a 3 to 4 year period, through these multi-day stakeholder engagement sessions and working with partners, working with emergency managers at state and local levels, working with our federal partners and working with people like Dr. Jim Porter from New York City DEP, across the board, 5 themes came across to us that we needed to work and improve the information we provide at higher resolution, with greater fidelity, with more specificity on the impacts across these 5 sectors: flooding, water quality, water availability, drought, and climate change. Nothing like setting the bar high for a federal organization. Out of this has come what we call the NOAA Water Initiative, which is setting us up for a multi-year funded effort to begin to tackle each of these compartments. At its root is going to be the development of our integrated modeling and prediction, which is going to be based around the National Water Model. But we know we need to expand the observations and data, which is why the effort here in New York is so critical. That precipitation and wind and temperature data is going to be critical to our ability to assimilate rainfall and temperature and to help that drive the hydrology as rain events and snow events come through. And through it all, we want the outcome to be new, integrative, and innovative decision support tools to help us deliver better services. This is what, jokingly, we kind of call the stairway to heaven diagram. This is, if we get all the funding we ask for, and we get it all right when the stars line up, the grass will be greener by the time we get to water quality. But seriously, this has what has come out of these engagements with our partners, that we organizationally, in the Weather Service, through our new Office of Water Prediction, has already begun to tackle the initialization of a centralized water forecasting system. That's the National Water Model. We're now beginning to look at flash flood hydrology and urban hydrology, trying to take that information from a CONUS scale, a statewide, United States-wide model, and begin to map inundation during hazardous weather events. And then at the end of the day, after we tap and link to the coast, to deal with the water quality issues. The hub of all of this activity is going to be focused at our new National Water Center, which is based on the campus of the University of Alabama in Tuscaloosa. Already, on your website, through our national centers today, we are running a new National Water Model. First time in our nation's history that we have a high-resolution 1-kilometer model running in real time, starting with an analysis, then providing a short-range forecast, then providing a 10-day and a 30-day forecast. The model itself is based off of the great work done by researchers in our organization and through NCAR, the National Centers for Atmospheric Research. And this just gives you a snapshot in the various components, starting with the forcings engine, that's all of the data assimilation, the NOAA-MP land surface modeling, terrain routing, and reservoir modeling to get us to a point of forecasting. From a visualization standpoint, in this graphic, you can see a couple of interesting things. The first one here in the upper right is showing you the model's assimilation of stream flow anomaly. So we can actually take a peek at seeing where the stream flows are running above or below normal. And then in the lower corner here on the lower right, you're seeing what that looks like from a soil moisture standpoint. So truly, we're just beginning to tap the output from this model, but it is going to revolutionize our services. As I said, the Mesonet work here in New York State is going to be a key player in that left-hand column with our data analysis and assimilation that is going to drive the hydrologic models going forward. We're going to run this, or we are running this on an hourly basis out to 15 hours, a once-a-day 10-day forecast, and a 30-day long-range forecast. But we started running this in May. By the end of July, our partners are already screaming, saying, why can't you give us a 10-day forecast 4 times a day? Why are you stopping at 30 days? Give me a year. Can you give me a decadal projection? So, you know, you pop the can open, and now you realize, wow, okay, our partners not only are keyed in, but they do have requirements. Now, in all of this, we know where the greatest uncertainty is. The greatest uncertainty in our ability to do this correctly is going to be in our ability to model the atmosphere properly, to get the temperature and the precipitation forecast as accurate as we can in time and space, so that our hydrologic forecast means something. I want to wrap this up and end by putting it into context for you. Here we have 4,000 river locations that we currently provide services at today. But that information really, as I said, is point specific. So if we drive down here to Springfield, Missouri, you'll realize that while we have a forecast point in Galena on the James River, there is so much more vulnerable area that we're not providing any actionable information on. That's what our partners have told us to begin to drive toward. Try to get us to a modeling infrastructure that allows me to provide flow, stage, and inundation forecasts for any one of those small catchments. And when you zoom in, the beauty of today's GIS infrastructure is that we can then map that to what's on the ground, to the bridge networks, to the hospitals, to the schools, to the evacuation shelters. We're going to be running this model as we are today at 1 kilometer throughout the United States every day, but we will run nests, high-resolution nests at 250 meters that will allow us, when we have a large event impacting an area, to actually provide forecasts and map potential inundation of these small watersheds. To give you a quick example of what that looks like, this was an experiment that some students did for the Water Center this past summer, where they took the June 23rd dramatic flash floods that you may recall that struck West Virginia. In the upper right-hand graph, you see the water model's simulation, which in this particular catch was a little bit overdone. But when you look at the flash flooding that occurred, it was not a bad forecast. It had the timing, it had the right area, the magnitudes was a bit off. But again, this is version 1.0 of the model. But what we have tried to do with this is 2 things. First, map the stream flow with respect to its, respect to climatology. Is this a flow that's exceeding climatology? Is it exceeding a 100-year event? Now that we have a water model running at a high resolution, these are the types of services we can begin to drive toward. And the ultimate action for the local communities is to take that hydrograph in space and time and to provide some concept of what the inundation on the ground may look like. That will revolutionize what you folks in the media could do for us to help us get that word out in advance of these horrific flash flood events. Just a small example for you of where we're going. Already in place today, our river centers nationwide are implementing a new hydrologic ensemble prediction system, which will allow us to provide forecasts out to 1 year. We are, thanks to New York City DEP, my office and the Mid-Atlantic River Centers, we're acceleration offices on this new technology. So you're going to begin to see some of these new forecasts roll out. We're going to be working with the Water Center to stand up a new national water resources data service and a validation service. In retrospect, due to the funding issues and the desire to get a water model stood up, we were forced to put on the back burner the validation of the model and the standing up of the services to deliver that new information. So we've sort of done this a little bit in reverse, but where we are at now is securing the architecture to begin to stand up that service that'll more effectively deliver this water information to our partners, and more importantly, to do the validation of the model, this first iteration of the new national water model. And this will be a continuing process, increasing in scale as we develop more experience with the model. And then the National Water Center itself will be standing up its operations center during the next fiscal year, and they will begin to work at the national level with our federal partners, whereas our river centers and offices like Ray here in Albany will be working with you folks at the state and local level. So, thank you.
Thanks, Dave. It's pretty exciting stuff. I'm actually pretty excited about seeing some of this stuff roll out. I wanted to open this up now to questions for the second three panelists here, Dr. Joseph, Raymond O'Keefe, and David Vallee. If there are any questions, go right ahead. Sure.
And my question, I believe, would be for David. I was watching the hurricane about a month ago that came up through Florida, and they had a system in place like for Jacksonville. I'm familiar with a lot of the communities there, and they showed where the storm surge was going to be, and it was fully integrated into the news reports on a certain national channel. So is that the type of system that you're talking about? Is it in place already in Florida?
From a rainfall riverine standpoint, it is not, and that's one of the limitations we have with our current architecture. It's taken about a decade for the storm surge information that you're referencing in Jacksonville to reach a point of maturity where it could be very seamlessly put out in the TV and as part of their broadcast information. We envision doing something very similar as we move the hydrologic forecasting forward to get us to a similar point. I would love nothing more than to have him be able to provide for you a projection of what the inundation might be on a river or stream when we're forecasting a rainfall event.
Any other questions? You know, I was going to ask one question for Ray, if you don't mind. I really am excited about your new progression to the watch and warning to make it simplified. Do you have anything in the works, or has been talked about, to do the same thing, because that was for winter weather, for severe thunderstorms in terms of watches or warnings, and not necessarily to simplify them, but when we do probability forecasting, the percentage chances of these things turn out to be so low, like a 5% chance of a tornado, people might just write that off. But how do we express that better as that being actually a pretty good chance at something that might happen during the course of a day?
Yeah, Paul, I focused on winter because of the nature of the conference here today, but the hazard simplification process, I showed that the elements up there, the periodic table, and that's everything we do, you know, across the board from winter to summer, water and weather. The intent of weather simplification is across the board to simplify the entire process. I know hydrologic warnings are being simplified. In fact, one of the driving forces for this simplification process was the service assessment done for Irene, where it was stated, you know, that there's this plethora of hydrologic warnings that basically all tell people, hey, it's going to be a flood. And so the concept is to look across the spectrum of weather service watches and warnings with an idea to simplify them all.
Okay, thanks. Anyone else? I think we're all set, yeah.
So I'm going to try to remain audible here. First, thanks to Paul Caiano. And all of our presenters, our partners, and special thanks to our staffs. That concludes our program. Thank you.